I'm starting the stream. Hi, Math2222, and thanks for making this cat fractal. Surprise! Thanks for in between streams, Math222 in chat there went in Desmos and did better at Desmos than me again, and made the cat fractal, which is a fractal we invented last week to make a point about finding the areas of fractals with overlapping sections. Good to see you, and hi to everyone who's watching. It's going to be one of those chill math streams, I think. That's the plan. I realised that you could do a point that you could make with the cat fractal is something like there's one you could work out what the area would be without the overlapping, which would be 1/2 for the sort of largest triangle, plus 2 times 1/4 for the two. No, wait, are they quarter? 2 times 1/8 for the smaller triangles, and you'll get a kind of geometric series, which I'm just going to finish this idea, I think. But you have these 4 of these. It's me drawing it terribly over the top. 4 of these triangles. So if there were no overlapping, I think this is going to be 1. Let's have a think. So this goes down to 16, and I get a quarter. Oh dear, maybe it's going to diverge. That would be fun. No, because it's half of 1/8, so it's 32 down here. Right, so each time there are twice as many, but they are. Hey, hello, Mimichin Rex and Murray and Herb. Good to see you. So the number of them is 2 to the 0, 2 to the 1, 2 squared, and that continues. And the size of them is 1/2. 1/2, so this is 2 times 2 squared. And this is 2 times 2 to the 4. So my sequence is something like... Sorry, I'm putting loads of powers of 2 in because I think it's a geometric series. So without overlap, the whole point of what we did last week was to think about the cat fractal with overlap and how its area is 2/3 of the unit square it sits in. And without overlap, it'd be cute if this added up to... It'd be cute if it added up to 1. I'm not sure it's going to. Let's find out. I am not good enough at this to do this. Okay, so there's a big factor of 1/2 at the front, and then 1/2, and then this is 2 to the -1, and this is 2 to the -2. Oh no, this is fine. Hello, thank you for the follow, non-wizard too. You might not be a wizard, but you you are a follower. I don't know. What are we doing? Good to have you with us. So I think this is going to be 2 to the -3 next for the next term in the sequence. That there are 2 cubed, 8 of the next triangle down. 1, 2, 3, 4, 5, 6, 7, 8. 8 of the next triangle down, and they've each got size. They are half the size in each row. So it's 1/4 of 1/4 of 1/4, or something like that. So I put 4 cubes down here. I shouldn't have done that. 2 to the 6, 2 to the 3, 3, 7, 2, 4, 2. Yes, good. Okay, well that does add up to 1 then, so that's good. Yeah, you might. It was the 2 suffix that threw me. It was like, you're not even the only not a wizard, but I'm not a wizard either. So there we go. Okay. Mimichin Rex wants the Discord. The Discord's not official, and it's unofficial in the thing there. Always be really careful with Discord, and I kind of feel like a bit Discord in particular. You don't know who you're going to meet, but that's also how this works on Twitch. Right. I tell people a lot at work, where people were using for the official live stream for Oxford. You can set your username to anything, because we don't want people to have to use their real names, because real names is a headache. And then people started setting their names to celebrity mathematicians, and this was a problem. So we had a lesson. Lots of people learned a lesson that day, which is, no, that's not really celebrity mathematician in chat. Anyway, Herb getting some admin work done. Mario's sleepy. Yeah, people they're talking to each other in chat. Right, okay. So I quite like this as a sort of punchline. Well, not a punchline really, but I don't know. Oh, that's interesting. some of the text gets associated with a fractal and some of it not so much. There's another fact about overlap for you there. Okay, so the cat fractal is an example where you draw infinitely many triangles such that the triangles would fill the whole space. Maybe that's obvious if you rotate them or something. Maybe that's obvious. The triangles would fill up the whole square if they weren't overlapping, but because they are, the area of the cat fractal is something smaller than 1. Maybe that's the way in to start talking about overlap. To say, you've seen this before. We had a big square and then 2 half size and 4. Oh, they're not half size, are they? They're quarter size. Wait. They're not half size, they're quarter size. 2 times 1/2 times a quarter plus 2 squared times a half times 1/4 squared. I think I may have done that geometric sum wrong. We're going to have another go. The first one is size 1/2. The next one down is not 1/4, it is 1/8, but there are 2 of them. So the sum of the first 2 terms is 3/4, because if you span that triangle around, it would be 3/4. Oh, why is it called the cat fractal? Because it looks like a cat. It's got a little tail, it's got a body, it's a cat looking this way. And then the next level down, there is a cat. Oh, all of the cats are facing. Oh no, half the cats are facing. So then the next level down is there's a cat that is sort of facing the other way in here, with its tail sort of down here, and a second one down here, and they sort of continue backwards and forwards, left and right. We did this because we were trying to understand a paper online about the size of the Pythagoras tree, which is a really interesting fractal, which someone worked on. Actually, not last week. I found out about it last week, but I saw later it's published November last year or something like that, or possibly earlier, last summer. The Pythagoras tree. Let's see if we can find it again. The Pythagoras tree is this one, where you have a square at the bottom, and then your favourite isosceles right angle triangle on top. That's not part of the fractal, that's just a spacer. And then 2 squares, and those squares are the start of 2 copies of the Pythagoras tree, so you keep going, and it curls around and it overlaps. And the area that you end up colouring at some point, that's inside some square, is rational, and it is this rational, which is an amazing fact that we looked at last week. The paper is great, but to understand the key idea about fractals with overlapping areas, we invented a new fractal. So we invented our own fractal, which is this one, a big triangle, and draw 2 triangles on top of it, pointing the other way, and then repeat on each of those triangles, 2 triangles going down. And then people in chat noticed that it looked like a cat. Yeah, so the area for that one, for Pythagoras, is the Pythagoras tree turns out to be rational, but a mad rational. So if you were here last week, you saw some discussion about why this is. There is a good reason that these things are. Its area is a kind of. If you split it up into little bits, this is just going to bury the point, isn't it? But its area is a linear combination of the areas of those parts. You just add them together. They're smaller, so they're kind of like copies of parts of the big picture, but smaller and added up. And the observation is that you can only see finitely many things as you zoom in, because even though there's overlapping, that's just some combination, so some subset of parts of the tree superimposed on each other down there, that as it gets really complicated in here, it doesn't sort of get infinitely much. No, it gets infinite. You get arbitrarily overlappy, but you can express that in terms of a finite basis. And then the paper uses some lovely charts of finite automata to describe the linear relationships. Good. Right. Yes. So it's mad that it's rational. The cat fractal, with all of its overlapping triangles and bits that are inside both or 2 or 3 of them, turns out to have area 2/3. which is a nicer result. So I feel like this is a good warm-up problem. And we did this last week to build our own little argument to say, as you look inside each corner, 1, 2, 3, 4 corners of the shape, what do you have inside there? Maybe you have like full body of the cat fully coloured in. Maybe you have clear air, or maybe you have a triangle and a smaller copy of the cat. It's important that it's both. There's still part of this enormous triangle, if you look in the top left corner, big triangle, but also a cat facing the other way, and they superimpose in a complicated way. So there's these combinations of what we've got, but not that many pieces. Okay, they can overlap, but not that many. So you considered combinations like if you have a cat and a triangle and a full body bit, which would then, because of the full body bit, that's just area 1. And there's a linear combination going on, and we had to solve some equations, and we got 2/3, which also seems to make sense. It was good. I liked it. I still haven't seen this sort of take off on the web, so possibly I should actually put some effort into doing some maths outreach based on this. I don't know. Ginger Snap was the winning biscuit last week. That's a good biscuit. I like a Ginger Snap. My students are already keen on Kit Kat Chunky, which is a thing. Did I say that last week? That's the sort of thing I say a lot. It surprises me a lot how keen they are on Kit Kat Chunky. Possibly because that's what I give them. I gave them Kit Kat Chunkies one time. They were like, yes, that's fine. Keep doing that. So, no, I respond to feedback. Good. I've never had a Ginger Snap. They're not very, what's the word? Exclusive? You can find a Ginger Snap. It's quite a hard biscuit. Taste of ginger. Depends how much you like ginger, really. Right, okay. So my plan, I think, is not to try and make this. I'm really glad that... Thank you to Maths22222 in chat for, in between streams, putting together this Desmos image. I think that needs to be an emote. I don't know what the emote's for, but we have this small menu of square images that you can paste in chat called emotes, right? And we currently only have a few. And we've just found a square that I think is like a cute cat, so that's got to be one of them. I've no idea when we're going to use it. We have quite good codified rules at the moment. Like RFL is the one for celebrating a win. Hardly ever comes up. Oh no is for when something goes wrong. That one comes up. Twitch just told me before I started that's my most used emote. Most used emote. Oh no. And we have wow for if something's actually good, which Herb used when Herb solved the Pythagoras tree. There you go. Good. Maybe it does need the :3 on it. I've worked out the eyes need to be higher than I think, like here. Maybe the little ears. Have we been doing this for the tail as well to try and hide the fact that the tail is like quite complicated? Anyway, I think the first couple of generations look especially like a cat. So you have the big triangle and then the second level thing. And that is not a bad rendition of a cat, really, by my standards. If I drew something with little cat ears and a tail, I might draw that as a sort of very minimalist cat. And then it sort of devolves into fractal nonsense, right? Good. Wow and Ruffle are the best. My emotes were all very weird. I don't really know what emotes are supposed to be. I know Mean Machine Rex is very into emotes. You have your emote codes that somehow don't render into emotes for me on my screen. Yeah. It is an oddly fluffy cat. One of its ears is really, like, don't look too closely at one of its ears. It's got this little tuft of hair, which is also made of cat, I guess that is the thing about cats, isn't it? Right, okay. What we're going to do, so that I consider that kind of done in a way. I'm not going to go in and analyse their 10,000 linear equations. We were lucky, we had 2. For the Pythagoras tree, they have about 10,000 equations. I'm not going to go and try and work out the coefficients. I had a thought that that's it's the audacity of the proof. Sorry, can we go back to Pythagoras tree just quickly? So it's the audacity of at some point we consider 2 to the power of 116 plus 1 states, which is finite, And the key thing is that it's finite, that this is only so many things that will have a big linear algebra problem in perhaps that many variables. It turns out to be only about 10,000 or even really 1,000 if you like. But it's the audacity of saying, oh, well, I just consider all combinations, right? There's only finitely many, it'll be fine. Tea biscuit emotes would be cute. Tea and biscuits. There's a lot of biscuit chat going on at the moment in chat. And we do have tea breaks. I've tried to set the image that you have for redeeming tea time. It's supposed to be a cup of tea. But I think it's such a bad picture of a cup of tea that no one's ever noticed. Right, good. Okay. Go on then. So Mean Machine Rex, if you... Yes, cup of tea would be the... I think there's a cup of tea emoji, isn't there? But it's like green tea, so, which some people are into. Maybe cup of tea emote. Surely some other streamers have got a cup of tea as an emote, right? Can we steal theirs? Or use, but borrow theirs? Can't be the first British person on Twitch, right? It's Piffing Brit, right? Did they have a cup of tea emote? They must have. Anyway, never mind. Someone who's really leaning into it, right? They should have the cup of tea emote. Oh, is that a cup of... is that actual coffee? How's that render on there? Oh, that renders much better on there than it does on there. That's fun. Oh, I have to check my emotes in different screens. Okay. Thank you, Rex. Vaguely T-shaped. That's also what people say when I try and draw T. Right, okay. I do want to go back into Hatch's topology of numbers. I updated the what command for this because it was just getting good, wasn't it, with quadratic forms. Before I got distracted by Pythagoras and fractals. That was nice. Wait, I didn't finish the geometric sum. Finish this first. People have pointed out on the stream that I start more things than I finish. Wait. So how many fours have I got? Maybe this is one. Or maybe I'm back to being happy again. How many is this? Two. Oh, just oscillating the emotions. No, I'm back to being sad, I think. Because 16, 32. Yeah, no, that's an 8. That's an 8. Oh, okay, now I think it's 1 again. Back to being 1. Right. If we get enough emotes, I've got a button. I don't think I've ever hit it, but there's a button on the Twitch dashboard that sets chat to emote only, which sounds very funny. I don't think we've quite got enough yet, but possibly we can reduce all conversation to just a codified series of emotes, which feels like the aim of Lean as well, right? To have a codified axiomatic system where then all communication can be expressed through very small symbols. Combined together into arbitrary strings. So possibly emote only mode is where we're headed. We can like fully axiomatize Twitch chat and then just have like a fully logical system where we just have to use the right emotes in the right order. In order to set this up, I tried to upload some logical quantifiers as emotes, but Twitch blocked some of them because Twitch thought that some of them looked like letters of the alphabet. And you're not allowed letters of the alphabet. Yeah, the two sides of humanity. Wow and oh no. The only ways you might react. Okay, I'm going to try and get Hatch's topology of numbers on screen. Yes. Try being the operative word. That goes there. That goes there. This goes here. This goes document. Oh, they've moved the button. They've moved the button. Chat. Connect to app. Accept. Yes. Why is it so small? Right, let's hatch this topology of numbers. We're going to be fine. We can read that, right? Oh, look, it's got that picture of a tetrahedron. We were discussing last time. Let's see. So grab it here, can't I? We were discussing last time that you can draw a cube on the faces of a tetrahedron. Is that what we did? And then a dodecahedron on that? Was this sort of weird glyph going on? I think we'd got distracted from our mission to understand number theory fourth time lucky. People new to the stream, hello, welcome to the stream. I've had about 3 or 4 attempts at understanding number theory. I'm not a number theory sort of person, really. Well, I know I've never got past about a sort of second year undergraduate course in number theory. And I'm having another go with this book, which has lots of pictures. Somebody recommended it to me as a picture. Wait, yeah, somebody recommended this picture book to me. It's not quite good. What's your take on the scale from oh no to wow? That is a good question, Mary. We do a survey. We do a survey for masterclasses where the options, instead of numbering them 1, 2, 3, 4, 5, we have the little smiley faces. Except the challenge there is, I'll put some in chat for what we had for the good options. No, Twitch is gonna correct them for me. I think people call these something else. I have to undo that. Okay. So we had 5 symbols. It's done them all into robot emoji. Annoying. So :D works for very. I had a great time in this session. We had : close bracket for okay, well good I suppose. : for medium. : open bracket for sad. And the idea was we wanted a 5th to fill it out, and then the solution was : C, which I'm very pleased with, but which nobody has ever actually used. I don't know. Did people in chat? You can tell me. Let's find out if Twitch recognises it. Is it a real thing? No, that one's not real. We invented a new emoticon in order to give people an option to say that they'd really not enjoyed a math session. It looks like a seal. Yeah, : small c. Small c looks sadder somehow. : capital C is almost shocked. Right, okay, good. Good feedback. Thank you, Twitch. I'll go back to the. I'll say we've got our emoji team are on it. They've got back to us. They say : small c. Right. Enough of that. People want the maths, maybe. Who knows? It's chill maths, isn't it? Right. Okay. So we're looking at a diagram which has got around the outside all of the fractions. They're arranged in sort of a mad way, but the way this book arranges fractions around the circle works like this. You put 1 over 0 here, yeah, I know. You put 0 over 1 here, and then halfway in between, you put the fraction where you've added the numerators and added the denominators separately. So 1, 1, because you add the numerators, you add the denominators, you add some 1s and 0s. And then halfway in between, you do the same process. You add the numerators and the denominators, and you keep going like a sort of binary tree. So halfway between 1, 1 and 1 over 2 is 2 over 3, because you add the numerators and the denominators. This is not how adding fractions works, but it does get you to all of the fractions. That's not obvious, we had to prove that, but it gets you to all of the fractions. And then the plan for this chapter is that we're going to try and understand quadratic forms where you have 2 numbers going in that are coprime, perhaps. It's not very exciting to put in numbers that are not coprime. You just get multiples of what would have happened if you'd put in numbers that were coprime. Yeah, okay. So for our quadratic form, we're going to plug in the numerator and the denominator, which for me really makes me think that we're thinking of these as a pair of numbers rather than a fraction. But never mind. Okay, we're going to plug those in, and there are regions in the circle, which is new for this chapter, so it's something for me to understand, that are labelled. Now, how does this work? So, oh gosh. I remember we had lots of curved circular arcs joining up things that had been combined. And these are the duals of those. So this circle has turned into just this line crossing the boundary, connecting the middles of the regions, if you like. There's a diagram of that back here somewhere. So yeah, we had all these in grey circular arcs, and then you get these triangular regions, triangular in the sense that they have 3 sides. Mark the centres, or something near the centre is topology, it doesn't matter. And join the centers if they share an edge. So you get this binary tree. Binary tree. Good. Oh no. Wait, hang on. So in chat they've worked out how to do this. What's this? Oh, just colon sad, and they put but they've got flat line as a very neutral thing. Okay, I think that's fair enough. Yeah, flat line in the middle. Mary's got flat line as well. Moon Machine's got. Okay, so for the robots in Twitch, the medium option is vertical line. Oh yeah, that thing. Right, good. Okay, emoticons. Right. Is that supposed to be a rendering of my eyebrows? No, I'm reading too much into this. Good. Okay. It's fun seeing which ones Twitch recognises, right? Okay. So you get these regions, and there's a region for each fraction because. Oh, I can't just say because without thinking about it. Now I'm a bit stuck. Why is there a region for each fraction? Well, each fraction has lots of grey arcs coming out of it from where it's been combined with stuff. So those will define edges of a region, but it can't get cut off entirely because these edges are going to come in here. No, terrible. Say it again. There's really a lot of edges on this region, so let's not think about those. Why is this region necessarily connected to the fraction? Oh, this is all right, I suppose. As soon as you mark in this fraction, you know that this area is going to be always associated with that fraction, because as things keep happening, you'll always be able to come in here in between and get back to the fraction. And there's never two fractions on the same region because I'll connect them, and then the connections, if I had two fractions, there's always something in between, and the in-betweenness would be an arc which would then have a barrier on it, I think. Right. Okay, so we've written in some numbers, and the numbers are the values of x squared plus y squared. And the observation, I think the cliffhanger we left this on, was the fact that across this shape, anywhere you see it in the picture, like, where's a good one? Here, 2, 5 and 13 in the middle, and then 34 on the other side, those form an arithmetic progression. So it goes 2, 18, 34, which is an arithmetic progression with common difference 16. My goodness, which we proved by, I mean, the proof looks really straightforward, but it's in fact based on our deep understanding of what the relationships between the fractions that are being joined up are. They use the median property quite a lot, right? Similarly for the other edges. So this is a good rule because it helps you fill in the picture. But the proof is quite algebraic. It just says, by, I suppose, topology, we know that the things next to these, the fractions next to these, are the ones that are connected to both, and that happens when you do the median rule thing to put in the midpoint. And the difference happens because maybe that's the midpoint of those two. This chat trying to work out how to feed me other stimulants. This is a worrying turn of events for Twitch chat. We have a redeem tea button that causes us to go and take a break for a cup of tea. Twitch chat has realised that this technology could be abused. Good. Cool. Right. Yeah, okay, so based on our understanding, I still find it confusing that that one is the median of these two. So what's this with minus signs in? I suppose this is a number such that this is the median of those. No, this is the median of them. So you take this and that, and you median to them by adding the numerators and denominators, you get theirs, which is why they're connected, connected together. Don't love it. If you take this? Is this one? Is it the same the other way around? Not really. Because I have to add x1. Oh, you can flip both. Because you can multiply top and bottom of the fraction by -1. Flip both, and that's the same point. Yeah, okay. Okay, I don't love it. But it's playing with the idea that the fractions are equal if you multiply numerator and denominator by -1. We've taken integer pairs and done quite a strange sort of quotient operation that I'm struggling with. Some of those are negative, right? It depends whether x1 and x2, which one's larger? Oh, negative denominators? Nothing in my fairy circle is negative denominators. Okay. Well, let's ignore that for a minute. There's some algebra to actually go and check that the arithmetic progression thing works, which is fine. We hit some exercises, but we're being too chill to do exercises. It's find all solutions of this, which is fine. This is very computational at the moment. It's sort of, here's a different way to label all the regions in a complicated diagram. So our quest, I think, is to understand which numbers can you make, and this gives us an algorithm for filling in the diagram, but it's not at all clear to me which numbers you're going to get. So it's not at all obvious to me that we're going to get any solutions where qxy is 24. I've got to really think about it. Okay. Or draw in some numbers and then see if I get 24, which feels a little bit like checking. Okay, hopefully there's something coming up that's sort of a point to do this. We will see. Right. I'm going to risk having more light. Oh gosh, that's quite bright. Oh, it is gloriously sunny. Yeah, that's all right, isn't it? Phil, I think they call that. Good. Yeah, gets rid of the weird glasses reflection thing we had going on. Good. I spent too much time looking at my own little corner of the thing. You know when you're in a call and you're talking to someone on the call, but you end up looking at your own video feed on the call. I think that's also a thing for streaming, except it's sort of a one-way call. It's like being on a call where the other person doesn't have their video on. So it's only me. I've got 2 or 3 copies of myself with various time delays. It's very distracting. Right. Okay, but I have other stuff on the screen as well, right? I have maths. I can be looking at the maths. Sorry, I've weirded myself out about streaming again. We're back, don't worry. There's a chapter called Periodicity here. Look at that picture. Isn't that nice? Oh, forest. Lots of binary trees growing next to each other. Oh, our binary trees are organic, ethically sourced. Some of them grow downwards as well as upwards. That's something we like. Right, good. Okay. For most quadratic forms that take on both positive and negative values, such as this, there is another way of drawing the topograph that reveals some hidden and unexpected properties. That is what we're here for. We are always here for hidden and unexpected properties. Let's underline that as an exciting thing to be finding out about. Looking back at the one we drew for x squared minus 2y squared, which was, right, flip back over here somewhere. Here's one. It's got negative numbers and it's got positive numbers, and they highlighted this separator line. I'm going to put that in red, I think, just so that we've got the separator line between positive and negative values. Our prediction is that that's heading towards square root 2 in some sense. I don't really know what towards means, but root 2's got to be around here somewhere. In terms of value, yeah, the fractions do have similar values. If you pick 2 fractions that are very close together on the circle, they've got similar values. Ish. Except for the ones near infinity. It's a projection of the real line, so around any point there exists some neighbourhood where you pick it for every epsilon there exists a delta. It's fine, so it can be near in some obvious sense. It's me trying to put a metric on it. It's good topology. Maybe I'm not supposed to have a metric. Maybe I shouldn't want a metric, but hey. What is going on in chat? Anyway, looking back at the top graph, there's a separator line, which is this. I'll mark it in red here as well, I suppose. That's not red. Mark it in red here. Yes, new feature. Love it. Love it. Straight lines. Good. If we straighten out this path through a line called the separator line, what we see is the following infinitely repeating pattern. Oh, that is good actually, isn't it? I've just noticed the 7s and the 14s and the 17s. Here is the field where I grow trees that say 2, and you walk down the line and the trees say 2. What's going on underneath the line trees that say -2? So what's going on? Why are there so many 1s? This is going to be a sort of version of that arithmetic progression fact, isn't it? That there's a 1 and a -1. And as soon as you've got a 1 and a -1. Well, maybe we're supposed to start with a 1 and the -2. So the values of, if you plug in 1, 0, and if you plug in 0, 1, then you get 1 and -2, which let's say is here. Oh, here we go. I'm just one sentence, not even one sentence ahead. And they plugged in Q11. Can I see why they've plugged in Q11? Okay, I guess you get. Okay, I guess you get -1. And then arithmetic rule gives us this 2 here, and then these sum to 0, so you go across the X shape and you get -2, and it continues down. And then up here, well, you've got a repeating pattern now, so all these trees are going to be the same. And they're symmetric because there's 1s on both sides. So you get all the nice symmetry going on, and then some actual values. Okay, so this tells you where to find the values, maybe? It tells you that the values are going to be... Oh no, I was going to say around the edge of the 1, but no, there's a 17 that's not connected to the 1. That'd be too easy, wouldn't it? But the values live on that binary tree. Okay, so if I want to find the values that the quadratic form can take, I only need to explore values on these binary trees. They've now been unwrapped, so it's not at all obvious to me where these things are. So the rule for getting to that region is you do the mediant, which is a bit like adding together the vectors. So if you see a way to make 1 by looking at 1, 0, and a way to make 2 by looking at, how do you make 2 off this? Well, let's find out. So, no. Oh, crikey. So I need an X shape, and then it's the median. Is it the median of these two things? So that's 1, 0 and 1, 1. So 1, 0 gives value 1, 1, 1 gives value -1, and then something like this is the median. This fraction corresponding to this region would be the median rule of those fractions. But instead of fractions, I'm thinking of them as vectors. So I'm just going to add the vectors together. So my prediction is 2, 1 gives 2. Okay, so I think we start with a basis, and then we make everything else by taking sums of the things in our basis. You can't sum it with itself. This is mad, isn't it? There's a binary tree structure to how you're doing the choices. Oh no. Oh no. Well, this is true because 4 take away twice 1 is 2, so it's the value there. I am adding these to get to here. Then am I adding them to get to 7? What am I adding? So to get to 7, that's the other side of... so I need to read this as like... I couldn't find the cross shape there because I was looking for something like this shape. But because it's been straightened out, it's here, 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 and then sideways like the splits. Here. Maybe not quite that far, but... So this says you have 2 and a 1 over here. Why is there another 1? Why is there another 1? How do we get to that 1? That's fun. So you would add across the 2 and the -1. 2 and minus 1, so 3, 2. 3, 2 gives 1, because 9 take away twice, 8. Ah, this is fun. So, right, so periodicity. This is going to repeat, and it's generating different solutions to here and so on. These are corresponding to the refractions that live for each of these regions. And as we go across these lines, we're using a sort of median property, which is sort of like adding together some combination of these, some combination of what you had before. And that's going to give us another solution later on for some larger numbers where x squared minus 2y squared is 1. We're going to find it by walking along the separator line to get things that are close to 0, because 1 is close to 0. There's some really hard. I'm finding it really hard to follow the cross-shaped things to get to the next one. So to go down here and then into the tree, and then add things from the tree to get out the other side. Yeah, I don't want to go up to the 7 anymore. I want to keep going sideways through this, which means going across a cross shape, which I was looking for cross shapes that were like this, really, because that's what they looked like first time we met them. We have this rule about how there's some medians around here. If these are 2 numbers, then this thing, where if you're keeping up, then in the fairy diagram we would draw circular arcs. We're now drawing lines that cross the circular arcs, so these lines are indicated that there would be circular arcs between all of these, and more to the point, there's nothing going on inside, so this is a triangle in the fairy diagram, so it must be in some orientation there because it's the median of something. And where are you going to put the median of x and y anyway? It's either going to be there or on the other side. So we should just keep calculating medians. We should keep adding together vectors. So 3, 2 gives that solution. Let's see if we can walk across. I can see this happening down here. We have these solutions, which I should be tracking these solutions as well, shouldn't I? So 1, 1 gives minus 1. I think they'll write the fraction 1 over 1. I'm going to write the coordinates for my inputs x and y, which I'm thinking of as a vector. We should keep walking over there then. I've got to track how to get the 2's as well. Yeah, okay, so I need the 1s and the 2's because I'm sort of walking along the separator line, really, dodging around. I'm going to have to keep track of how to get these minus 2's. This is going to turn out to be a matrix operation. The matrix is going to take some sort of little vector. I've written a covector, but the matrix is going to take some vector and reply with a new vector, which is also a solution. I think I've seen this before. This is a thing where you have a solution, 1, 0 works, and then there's a way to generate the solution 3, 2, and then these are related to approximations for root 2. So it's all connected. It's going to be 17 over 12 or something. You know, it's like 3 of these plus 2 of those. Something like that. Let's find out. Okay, so I can see these diagrams down here walking along the separator line. Let's put it in red again. Maybe not, since it's a small bit. Place these as shown in part A. Oh, okay, where's how you make this? So as you go, you get these kind of cross shapes, and you walk across. This is a cross shape thing as well. Around left bit, middle, right bit. We have a rule for walking across those, which says that the value you get is you add the middle things together, and that's the middle term of an arithmetic progression. So it's 1, 1 must be 1 for the other side, constant arithmetic progression in this case. So we can generate this sequence and sort of keep building it outwards for the upright trees and the downward trees. I do actually, because the university has signed a big agreement with OpenAI for ChatGPT stuff, so that we can all get access to ChatGPT plus education mode or something. Good-o. Yeah, there's the arithmetic progression. Keep going, keep going, keep going. What does it say? Keep going, keep going, keep going, keep going. Then we get a pattern. To get the rest of the top graph, then work our way upward and downward to get the binary tree stuff. There's a monotonicity property in the next chapter. An interesting property of the form x squared minus 2y squared. Negative values are exactly the negatives of its positive values. Would have been hard to predict. And x squared minus 3y squared doesn't do that. Fair enough. Okay. Oh, and this one, it doesn't have the same pattern of tree growth, right? This one has one tree and then two downs. There's a close connection between the separated line and the topograph of a quadratic form x squared minus dy squared and the infinite continued fraction for root d, which is where we're going with this, when d is a positive integer that is not a square. Yeah, if it is a square, you can factorize that expression by the difference of tree squares. And also I think this line is heading straight towards a fraction, so it will stop really quickly. Maybe? Something like that. We'll see what the top of the graph can be. What is this? Used to compute the continued fraction for root d. Okay. Right, this is going to link together loads of things now, isn't it? Here we go. The relevant portion of the top of the graph for x squared minus 3y squared. This book does introduce a lot of stuff. Here's the strip separating the positive and negative values. This is part of the dual tree of the fairy diagram. Of course it is, it's made of lines from the dual tree. So dual tree because the regions before are now connected by edges rather than being separated by edges. Superimpose the triangles of the fairy diagram corresponding to this part of the dual tree. So there'd be triangles where, to get back to the original fairy diagram, we have this map which shows us edges between regions that were previously connected. Should have dual graphs work. So this should be connected to all of its neighbours. All of its neighbours? Yes, including this one sideways. So then you get a picture like this. This one's very, very symmetric up and down, but it doesn't have to be. There could be more, couldn't there? So this thing with lots of trees down here, lots of trees down here would be more lines coming up this. Right, okay. Ignoring the dotted lines to the left, the infinite strip of triangles corresponds to the infinite continued fraction of this. Easier way using the quadratic form. For fractions like this, labelling the vertices along the infinite strip, the corresponding values of this are either plus 1 or plus minus 1 or plus minus 2. We can rewrite this like that. We're going to get large values of x and y, which means that x over y is going to get close to root 2. Yes, so they've divided by y squared, and this thing's going to get close to 0. N is not quite fixed, but not changing very much. Doesn't get very large. It's bounded. The equation x that implies x over y squared expression 2. This is an old math question. It's been used for the maths admissions test, I think, or some part of this logic. Since these fractions, the convergence of the infinite continued fraction that corresponds to the strip, this implies the continued fraction is root 2. Good. And then there's this one where there were more neighbours down here, I thought. More regions than there were up here anyway. So lots of lines in this diagram of a strip. Not really necessary to draw the strip of triangles. One can just read off the continued fraction directly from the periodic separator line. Oh no. Chat one ChatGPT stuff. I'm only using ChatGPT for work things. And it's not very good at any work things, really. We're trying to get it to do brainstorming for a project. It can say quite obvious things, which is fair enough, I suppose. It's a thing that's trained on stuff that's been done before, so if you're trying to do something new, then it can help you make sure you do stuff that people have already done. But yeah, and apparently it can draw you as a Ghibli character. So there you go. AI, definitely worth it. One can see in these two examples, not really necessary to draw the triangles. Yeah, you look at the rectangles, like this brick wall shape they've drawn, and count how many there are. And that's part of the continued fraction. It's like this one. I can see 1, 2. I can see how many neighbours it's got, right? So that's sideways, but then 1, 2, 3, 4, 5, 6, 7. So possibly the number is 6. Crikey, out by 1 errors. Here we go. And then 1, 2, 3, 4, 5, 6, 7. So possibly the number is 6 again the other way. Do 6 times the other way. Yeah, how many count the edges? Good. Okay, so this tells you can do the continued fraction if you've done some calculation of this infinite sequence, not periodic sequence, just using arithmetic progressions because we're just using a medians property. So it's like the kind of moral of the book, right? You do quite a lot of work to work out these numbers, and then that's the same thing as doing the continued fraction, which also gives you the number. Root 19 looks fun. There you go. Root 19 has that continued fraction. So, is this going to tell me about... I am a bit interested in continued fractions of square roots of numbers that aren't square. Bit. We've been told that, for example, this one goes 2, 1, 3, 1, 2, same forwards as it is backwards, except there's an 8, which kind of separates out the repeated bit. So it goes 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8. But in between the 8s, that's kind of the same forwards and backwards, and the 8s are nice spaces in that. Which means that the sequence snakes backwards and forwards. It doesn't have too many 8s in it. On the way back, you can think of the 8s as still being spaces for when you read it backwards. So if you read it backwards, 8, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2. That's why it's same forwards as it is backwards, but with an extra number at the end to space them out. That's allowed because it will just repeat. Good. 1, 2, 3, 4, 5, 6. Oh no, but these are separate things down here. This is complicated. So this bit has got, maybe I don't count both of those, 3, and then I look over here, maybe. This one 1, and then this one's got 2 new neighbours, and then this one has got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 3, 4, 5, 6, 8 new neighbours. So you get that 8 at the end. Okay, in section 5.1, I can't wait for section 5.1, we prove that topographs always have a periodic separated line. The is positive integer that's not a square. I wonder how. Maybe we'll show it's bounded and there's only finitely many things you can get, but doesn't look very bounded, does it? It's bounded by 19 and minus 19. Maybe that's relevant. Oh, that'd be a good way of doing it. Would that make it periodic necessarily? Yeah, because there's only finitely many. If you've only got finitely many numbers, then this thing that only depends on a previous few of them. Which way up is it? That might be enough. I don't know why it would be true though, so let's not think about it too much. Wait for section 5.1. What is going on then? This separated line always includes the edge of the topograph separating the 1, 0 and 0, 1 regions, since it does plus 1 and minus d. In addition to being periodic, the separated line also has mirror symmetry. This is because the form like this has no xy term, so replacing that does not change the value of the form. Reflects the circular ferry diagram, reflects the periodic separated line. I believe this. I thought top and bottom, above and below were looking different in some of these examples. We've got loads of stuff down here. It's 3, 4, 5, 6, 7. Yeah, loads of stuff down here and not so much up there. Okay, so I've misunderstood this symmetry then. Has mirror symmetry with respect to reflection across the vertical line through the 1, 0 and 0, 1. Oh, left, right. Left, right symmetry. Oh no. Oh no. Okay. See this palindromic thing going on, which is the thing we're trying to understand. Right, okay, but it's in sentences. Here we go. The form has no xy term, so replacing that by minus x over y. What's the separate line as symmetry with respect to this vertical line? The periodicity forces have mirror symmetry with respect to an infinite sequence of vertical lines, the dotted lines like this. Yeah, it's getting a bit much, isn't it? But it's almost tea time. I wish it was labelled. So this line that we're reflecting in, I mean, it's periodic, but this line that we're reflecting in is supposed to be special. It's supposed to be the one that connects the region. No, the one that I've got really flipped around by all this switching between regions and numbers, right? Where's that? Oh, there it is. It's labelled over here, so I have misunderstood. So 1 and minus 19. We need to understand why it's periodic. That's in section 5.1. But then the reflection here is to say, on the right you're plugging in positive numbers, and on the left you're plugging in negative numbers, but who cares? You were just going to square those things anyway. So left and right have the same things going on. And then because it's periodic, you get this palindromic stuff going on. A and it's 2A0. A0 is this collection of things. Oh, but this is going to be our observation. The last number is twice the first one or something? No. This thing is twice this. I feel like this diagram's labelled more stuff than we've understood so far. Is there more text underneath to explain this? Oh no, this just has to be... That's implied by the symmetry, isn't it? That's implied by the symmetry. This is the second time reading this that I felt like we're hitting on some sort of fact about periodic sequences that's completely divorced from like number theory or Fairy diagram or continued fractions especially. It's just a fact about what happens if you have certain symmetries in your sequence of objects, which was probably going to loop us back around to groups and symmetries again. But look, so they're saying there's a chunk on the front, but then mirror symmetry in this dotted line gives you a bit more over here of the same size. So you can see it better over here. It's periodic sideways as well, so I can just go and look over here instead. Minus 19, minus 18, minus 15, minus 10, but then reflecting to the left, minus 18, minus 15, minus 10, because this is plugging in negative numbers into the quadratic form instead of positive numbers. You go that way and you get negative numbers? Sure. But we also know it's periodic, so we know at some point this whole thing is going to repeat. And now, how do we combine these mirror symmetries and translational symmetries together? So it's a bit like proving symmetries of a cosine wave or something like that. Yeah, like a cosine wave, right? You have a reflectional symmetry in the x-axis, in the y-axis, sorry, reflecting in the y-axis. You have a reflectional symmetry, and you have a translational symmetry. And that gives you facts like 360 minus n, or 360 minus theta or something. You can combine those together to work out that this bit coming down here is the same as that bit coming down here, and possibly you can work out that this bit in the middle is palindromic. Right, yes, because stuff over here in this sequence where I'm drawing this cosine thing, you've got a reflectional symmetry and you've got a translational symmetry. What can you generate? Or it's not even that, it's like yeah, you've got two isometries that act on a long sequence of objects. and you'd like to know what set of objects you have remaining, like what are the possibilities, and in fact, you get to do whatever you like up to halfway before you meet the mirror image of yourself coming the other way. In here, so you can set these to -18, -15, -10, -3, flip over here, 6, 5, 9, 9, 5, 6, but until you get to the middle, sorry, at that 9, at which point, because of mirror symmetry and translational symmetry, you've started filling in numbers along this way as well. That's not a proof that that's consistent with both of the symmetries, except I should just go and check my answer, shouldn't I? Judge Murray has redeemed tea time, which means it's time for me, at least, to go and make a cup of tea and think about symmetries while the kettle's boiling. You might like to make a cup of tea as well. You might like to think about symmetry or palindromes. It's up to you. There we go. This is going to turn into a very tidy proof, isn't it? Once we know it's periodic, which we haven't done yet, but once we know it's periodic, then the continued fraction part of the square root of a non-square is going to have to be periodic and have that sort of extra number at the end, which is twice the number at the very front. Yes, right, for Yorkshire. Okay, good. Yeah, this is some text to explain all of that. The final 8 is twice the initial 4. Midlines, got these symmetries, very good. Less apparent, fewer terms. In some cases, an additional symmetry? No, wait. A little palindrome in there? Yeah, fair enough. Extra glide reflection. I think I'm starting to understand why they did so much glide reflection stuff before. Because, well, it was relevant to the sequence and the continued fraction before, and now if we can prove that something is periodic like that, we'll know that we get the same sort of continued fraction property. Fair enough. Okay. Right. Yeah. Chat's right. We're gonna get some tea, I think. Glide reflection twice. Yep. Okay. This is turning into observations now, isn't it, about what's going on inside here? We're going to come back for this bit. Everything works just fine for PLQ. No, not excited. I need something to be exciting for when we come back. Yeah, change this. We'll prove in the next chapter again, look, in the next chapter, that this thing always has periodic separator line. Yep, okay. And the roots are irrational if you can keep going forever. Yep, okay, good. Here are some more pictures where it's a little bit, trust me, like, trust me, here's the calculation. Is it bounded by the product of the numbers now? It does appear to be bounded by the product, or the very first thing that you calculate. It does appear to bound it. It's still my guess. I might try and think about that while the kettle's going. Is this going to be bounded by... So if I plug in 1 and 0, 29, like the maximum of these two things? No, so that one was bounded by the product. So maybe this is bounded by 290? It appears to be bounded by 29, so fun. Is this one good? We're looking at one more example here. 1, 2, 2, 1, 2, period of odd length. Corresponds to the existence of glide reflection. Okay, let's come back for this, but it's time for a cup of tea. I'm gonna run an ad break as well. As a reminder, any ads that you see long-term support charity, because if this Twitch channel ever cashes out, then let's go to charity. Right, good. Okay, I will see you in a couple of minutes with a cup of tea, I hope. Good. If for some reason you don't get ads, you're just getting a back soon screen. Sorry. Right, let's go. I always get good ideas as soon as I move around, which is not good for streaming unless we take this like on the road outside, just wandering around. Some people do that. I shouldn't give you ideas. Right, see you in a minute and a half or so. back, I think. Yes. I really think I might be. Okay. So, 2 cases. I skipped quite a lot of text there, didn't I? But 2 cases, depending on whether the fraction is bigger than 1 or not, which is a sort of message we've met before. Yeah, good to be back. Oh, Mean Machine Rex put a cat emote in chat that's actually rendered as a cat. Wearing little sunglasses. Right. Good. Have I understood why these are... No, this is not claiming that these are related. This is just 2 cases. Yep, okay, right. Look, okay. This is fine. I think this is only going to make sense when we've seen chapter 5.1 with its description of why this thing's periodic. Because at the moment, the thought I had over T, to be honest, was this has replaced the observation that continued fractions have these properties with the observation that the separated line in the topograph has these properties. So we've put some effort into trying to understand the separated line of the topograph, but I won't feel like it's paid off unless we understand why it's periodic in this setting. I agree that these things are equivalent. I don't understand either of them at the moment. I do like the way that kind of twice the initial number felt like it came up quite naturally from the symmetries. So I sort of accept that if we understand that it's periodic, together with that reflection symmetry at the start, then you can piece those together to work out these properties about the numbers relate to the topograph. So in the topograph, you've got this thing that's just doubly infinite and it's periodic and has a reflection symmetry. So you were sort of halfway through when you started. You're right in the middle on a line of symmetry, so there should really be an 8 going on at the moment in the sequence that goes 8, 3, 1, 2, 1, 2, 3, 1, 2, 1, 3, 8, 3, 1, 2, 1, 3, 8. But you were halfway through the 8, so you just saw 4 at the start, which is why the square root of 19 is about 4 and a bit. Sort of. I mean, not why, but consistent with the observation that root 19 is a bit more than 4. But I don't understand where that periodicity is coming from, and I think I've been told that it's not coming up until the next chapter. So I'm now trying to accelerate to get to the next chapter, because I think that's what I should be reading. But I want to see that there's not stuff in between. It's tricky. I could just skip to chapter 5, but what if there's something really important in between? There's no way to know. We're just going to plough through, I think, a little bit. Yes, right, so more generally, so there's motivation perhaps for what we're going to do once we've got these numbers. All quadratic irrationals, you see, so this is going to be how we understand quadratic irrationals. I think that's algebraic numbers that have come from roots of polynomials of degree 2. Let's find the continued fraction for this, which is root of the equation of that. Right, okay, good. This phrase quadratic irrationals to mean irrational numbers that are roots of a quadratic. The associated quadratic form is this, fine, and then multiplied by y squared. We would like to have a period, we'd like to find a periodic separated line in the top graph of this form. Oh, okay. So cool. Good to see you. We're reading Hatch's topology of numbers again. In the way that Hatch's topology of numbers will do. And it's useful for me to explain this to Seifel because it's also me explaining it to myself. Hatch's topology of numbers has invented another sort of diagram I hadn't seen before, and we're proving that the diagrams are related to each other, and there is a promise that next chapter we will prove something useful about the most recent sort of diagram. The book has lots of diagrams labelled with numbers and fractions, and the meanings of these things are quite context dependent. They have to have understood what was just going on for the diagram. But hopefully it's going to teach us about values of a quadratic form, so that's pretty good. Right, so we're going to find what they're calling a periodic separator line, which is a line between cases where you get positive values and cases where you get negative values for your quadratic form. It's not obvious where you're going to get either of those, is it? So if you put in 1, 1, then you get positive 1. Let me guess again. If I put in 1, 2, then I get... Oh my goodness, I don't want to calculate that. 4 times 7 is 28, but this is minus 80, so it's going to win and we'll get a negative number. Negative huge thing, I think. If I put in 1, 2, 4, 28. I'm only subtracting 40 and I'm adding 14. So 42 take away 20 is -2. Good. Okay, so I can make negative numbers. I guess I should complete the square to work out if I can make negative numbers or not. It's a blast from the past, isn't it? Complete the square. I love complete the square. To work out if this ever gives negative numbers. Oh, never mind. Okay, there's a discriminant, right? Oh yeah, we should do the discriminant of the quadratic. Will tell us whether this thing has roots or not. I suppose we're only talking about when we know the root in the first place. Anyway, never mind. Okay. Here's a separated line. The observation is that it is periodic along, so it's this line here, and the behaviour above and below is periodic. Sometimes you get a glide symmetry. Always you end up with at least a translation symmetry, and there's also a reflection symmetry going on. We have values when we put in 1, 0 and 0, 1, 14 and 7. Where have they gone? Oh, they're over here. Oh, interesting. Okay, so we have this 14 and 7 for putting in these initial values. They're both positive. And then we have to walk along here to try and find some other stuff. What's going on there? And it's not symmetric across this line this time because there's an XY time in the middle. I've gone a little bit gravelly. 1, 2. 1, 2. Oh, if you like that one, you'll love the one we had before. So it's a subset of the diagram because it's binary trees everywhere. The kind of fuller picture had binary trees. Oh, that was a good one. Sort of these things are roots of binary trees above and below. So we've had things like this where they grow into binary trees, but we only care about the bits where it's positive or negative for now. This is our favourite binary tree, which is the binary tree of all the fractions. And you might think, well, binary tree, the node at the top has only got degree 2. That's a shame. We thought of that. We've got all the negative fractions in a separate binary tree, upside down, and connected with a single line between the top. So we have this kind of binary tree for all the fractions because we're planning to plug in all of the pairs of co-prime numbers, aka fractions, into our quadratic form. So we're just sort of wandering around this binary tree of all the fractions, plugging in numbers and seeing if we get positive or negative stuff. And the observation, which we haven't proved, the textbook will do this in the next chapter, is that as you walk along that line through your binary tree, straighten it out into a straight line, you see something periodic. Good, right. I did a sort of UCAS fair on Monday and Tuesday. I don't know if I told you about it last week, chat. I went to London and stood on a stand for Oxford with some other Oxford people in a room that had basically every other university. So it's a huge hall in the Excel Centre, which is a big conference place in London where they do, if you watch Formula E, electric racing, Formula E do a thing at the Excel Centre in London. But normally they do big conferences. I was there on an Oxford stand and I must have talked to, I don't know, 500 people each day. It was just crazy. It was just like groups of people would come up and ask about Oxford stuff, and we would talk to them, and there'd be a mob of other people around. It's quite hard on the voice, but it's just sort of constant. You do because there's school groups and individuals arriving all the time and looking around all the other universities and then having a chat with Oxford. So it's the sort of event where you start at 9:30, they open the doors. And then the next time you look at your watch, it's sort of 3 p.m. and you've not breathed. Really good event. If you know anyone who's thinking of applying to university and they want to just meet lots of people from lots of universities quite efficiently, they do these things in other places in the country as well. But the London Excel one is the only one I know of that runs over 2 days. So there you go. If you know someone in London who wants to meet lots of university representatives without getting out of London, then there's a thing you can do. No! What have you done? No! There's no way I can ban that. That's ridiculous. And remove the space. I mean, come on. Right. Right. That's really annoying. Hang on, let's do a little notepad file. I'm going to have to go through all the diacritics. Oh my goodness. Tom Crawford, right? Yeah. Right. Wait, I timed out. Oh, Streamlabs timed you out for a thing. Did Streamlabs time you out? Hang on, right. DK. DMob. Why did Sensation Black get timed out? You only got timed out for a second. Was that because of something I clicked on, or was that just... It'd be very easy for me to click and ban the wrong person, and then I don't know what you do. Oh, you responded. I'm responding. So Streamlabs, my log says Streamlabs timed you out, which is my auto moderator, which is not clever enough to spot diacritics. Right, okay. Be nice. Right, okay. Where were we? We were looking at a case where it's not just square root d. There's some other stuff going on. Oh, I skipped so many pages just before the tea break. Brilliant, great idea. Because down here, look, 14 and 7, those are both positive. So this is not part of the separator line. The separator line is miles away. So you might have to walk in some direction. If your quest is to find positive and negative values separated by some sort of line in the binary tree, then yeah. Also, this is awful, but in the version we're currently looking at, the regions correspond to values you might plug in, and the lines correspond to edges between fractions that were connected in my binary tree. Not binary tree. Fractions are not connected in a binary tree. The fractions are connected in... Oh, I need a cup of tea for this, right. I'm pretending that I'm explaining to Sophal, who just said hi, but I think I'm mostly talking to myself. Here we go. We've got this really complicated diagram that's on the front page of this book. It's got lots of arcs coming out from each fraction, and they're arranged in a complicated order. But the picture forms lots of triangles because we've drawn arcs whenever fractions are connected according to a particular rule. And that rule, this was so long ago that we have the rule for connecting fractions. That rule gave us loads of triangles, which sounds mad, but that is what we did. We had, the very first time we did this, we had the fractions around the circle, and we were joining things up. And then we put the midpoints in. So the arcs were always to add in a midpoint between two fractions. We proved that this gets you all of the fractions, this kind of median thing on the middle. The very first time we did this, possibly the first stream we did on this book this year. So it's always triangles because you always have an arc that you're splitting into two. You have an arc and you put bump on it to join the median of these two numbers that you already have. So you always get triangles. So we join things up. Oh, is that a link to the picture? Thanks, you have correctly detected that I don't want to flip through and look for the picture. Thank you. Yes, we had all these arcs joining the midpoints. In this version, they are not quite in the middle geometrically for a different reason. This is a slightly different version of the picture, right? With the projection, we're doing the projection version, which I prefer. So yeah, there's a point somewhere in the middle. You connect like this, and then the triangles form a binary tree. And there's a line down the middle here. I'm just going to turn off the axes quickly. There's a line down the middle, so you get these triangles, and they form a binary tree because as you cross into these regions, you get these two triangles underneath. And then you have an arc, and the arc will inevitably have a region near it which is split by a bump into more fractal-like bits of region. And then onwards and onwards and onwards. Downwards. So you get this binary tree of triangles because the triangles have to form a binary tree because they have degree 3 and there's no loops. So you just freely generate this binary tree as you go. You have the way you came in, and you have 2 ways out, the other 2 sides of the triangle. Huh. Good. So they made a binary tree for the regions. And the regions have got numbers on now. And we've got lines separating them. And a rule for connecting these regions together. This is crazy. This is just crazy, right? And all of these have got degree 3. All the points have got degree 3 because they correspond to a meeting point between things showing you where to go from that. So this region. Oh, no. Now the regions are the fractions. Oh my goodness. We're in the dual graph. This is impossible to keep track of. Good. So for some reason we've wandered off in this direction through our chart or something with this line down the middle. We've wandered off in this direction because we decided that these evaluated to 14 and 7. And then we should go and look somewhere else. Which is a bit strange. No, I suppose not that bad. They're both positive is what I mean. But there's a direction you can go to... there's a direction you can go towards the mediant, always. So let's try and draw the dual graph on top in a different colour. We've got these 2 regions, which are connected in the dual graph because they're regions that share a border. And then there's a bunch more regions, of course, because these things are triangles, they're connected to 3 regions. So you have this going on, where the original nodes correspond to, in the dual graph here, sorry, these middle nodes in the dual graph correspond to these regions in the original fairy diagram, but now they're nodes. The regions correspond to nodes in the original diagram, which were the fractions around the edge. So before, perhaps we had these 2 up here, and now we have these 2 new regions splitting off here on the left and right, or whichever way around we're working. I think this is rotated by 90 degrees compared to the one on the front cover, but whatever. So we get this kind of elongated X shape. Like this, in here. So we've got 14 and our 7, but then we want to give numbers to, now I want to give numbers to the numbers on the regions, which are now nodes, right? Yeah, no, the 14 and the 7 belong in the dual graph because they belong out here somewhere for the values associated with these. They're regions in the dual graph. They're associated with points in the original fairy diagram because they're associated with plugging in some actual numbers into the quadratic form. And the numbers are written around the edge. It's just so much. The switch to the dual graph has completely thrown me in terms of how you talk, because we have to talk so like geometrically or talk in terms of the shapes that we have. And then the dual has completely thrown me because now everything that was region is a node and vice versa. Okay, so what's going on here? This will be the value when you move to plugging in 1, 1. And now it matters that you've got this term in the middle. I know that these things are going to form a arithmetic progression kind of thing because I've got this elongated X shape. But I think I need to actually go and look at what this number in the middle is because I haven't used it yet to fill in the 14 and the 7. So if I do that, then I plug in 1, 1 or something, and I get 21 minus 20 is 1. Okay, so then I have this property, right, that these things are supposed to form an arithmetic progression. 14 something 7. The something should be where what? What? Oh, do they not go across like that? This has got 14 and 7 in neighbouring things. Yeah, huh? Probably not that way around. Right, 14 and 7 were neighbouring, so I've labelled them wrong, haven't I? I was supposed to label them. Oh my goodness. This is okay. I'm supposed to label them up here and down here. Out by 90 degrees. They're separated by a line because they're connected with an edge in the original thing. 1, 0 and 0, 1 have to be connected with an edge in the original thing because they have to determine 1. There's this rule for connecting things. Be more precise. There's a rule for connecting points. They're labelled with fractions, or if you prefer, coordinates, A, B, and C, D. And the rule for connecting them in black in that picture is that AD minus BC is plus or minus 1. Could use it the ha emote, Murray, thank you. I forgot about that one. Okay, so it's 21, so maybe it's 1 and 41 or something? Like more positive. So you plug in 1 or minus 1, you get plus or minus 20. You get plus or minus 20 if you change the signs here. Plus or minus 20, so, 21 plus or minus 20. Okay. Not a disaster. I'm going to label it in here. 21, 1, 41 over here. It's all larger numbers. But if you keep walking, then you get towards negative numbers. Surprise. And then you can follow it out in either end. And it will join up to 2 things in this picture, which I think are going to be the roots of the quadratic. But the fractions labelling those points will be the roots, close to the roots of the, goodness me. The points you're converging to will be irrational numbers that will be pretty close to rational numbers that are actually in the fairy diagram. This thing is going to disappear fractal-like in both directions, linking together those 2 things. And you'll walk out this way and you'll find somewhere out there is a red separator line along here. Okay. The labels have both x and y increasing monotonically and approaching infinity as a consequence. Hence the values like this and the other one, are approaching 0 since the values of the numerator on the right just cycle through a finite set of numbers repeatedly. Oh my goodness, right, okay. Tell me that again. Hence the values. If we follow the separator line out to either end, the labels for both x and y increasing monotonically. You keep doing the median rule. Yep, so these values, which are like this. Oh, but it's periodic. We're using the fact that it's periodic to say that this quadratic form thing only takes finitely many values in this periodic stuff along here and divided by y squared. So if x and y are getting very large, then that's getting very small. Oh, so the value must be close to 0. What? I've misunderstood that. Oh, you plug in x over y and you're okay. The value of the quadratic form is the numerator over y squared. Okay, we're in the upper half of the fairy diagram. So limit on the right and the left. Okay, good. You get the roots. To get the continued fraction of the smaller roots, we follow the path in the dual tree of the topograph that starts. No, don't do the dual tree of the topograph that starts with the edge between 1, 0 and 0, 1, then zigzags up to the separator line, then goes out this line to the right. If we straighten out this path, it looks like the following, which is some stuff, I'm sure, and there's repeating things. Read off the sequence of left and right side roads as you go along the path. So this is someone imagining that they start down here, this line between 0, 1 and 1, 0, and they've got to get up to this separator line. And they're counting the side roads. So 1 on each, right? Just one on each side. then you're there. It's not actually necessary to straighten this out. Oh right, there's loads. Why have we got so many? I'm drawing in the continued fraction in grey underneath. Sort of repeating strip. Okay. Right, good. Yep. So you count it out, and that gives you the continued fraction. I feel like we've seen this before, sort of. Here's the proposition: it's eventually periodic. Although now you've also got to convince me that we get out as we go outwards. We do find a separator line somewhere. So that, I need convincing of that fact as well now. It's kind of obvious to me for the ones where you have x squared minus dy squared, because I can plug in 1, 0 and 0, 1 and find some separation. For other ones, well, it's not actually true that they always have a separator line, because they could be x squared plus y squared, which has no separator line. But for quadratic forms where there are real roots, I need convincing that there are values you can plug in that give positive and negative values. It's probably obvious, like plug in fractions that are near to the roots or something. Slightly above, slightly below. Does that do it? Maybe that does it. But I'd like to see that proof so that I know the separator exists and then we can go and find it. And apparently it's periodic, so great. We will show that the procedure in the proceeding as a whole works for all quadratic irrational numbers, and this will prove the harder half of Lagrange's theorem. The continued fraction for every quadratic irrational is eventually periodic. The other half is just algebra, which is the converse. If it's eventually periodic as a continued fraction, then do some algebra to simplify it down, and you'll get a quadratic equation with integer coefficients. But just like your periodic continued fraction repeats, so label the bit where it starts repeating as the same thing as the thing itself, and then work out what it means. And that's just lots of inverting and adding whole numbers. So you'll get some, I think we call them fractional rational transformation, but you got some Mobius map. You got some quadratic equation. Okay, it can't be a rational root because it's got an infinite continued fraction. That was the easy half. We'll do this hard half. But again, they want to convince me that this thing is periodic, and I haven't seen any reason why it would be yet. Here's a proof. Okay. I think this proof is going to rely heavily on chapter 5.1, which we haven't got to yet, so let's see. Strap in, everybody. Wasn't expecting a proof on this page, but we have used it. I'm going to lock in. No, I'm not going to lock in. It's chill maths, isn't it? Right. Okay, let's go. Proof will involve associating a quadratic form to each quadratic irrational. We'll need to use the fact that the quadratic forms arising as well will have periodic separator lines. Okay, fine. That's the thing in section 5.1. Looking forward to seeing a proof. Okay, yes, officially. This is, I think, at least the third time we've been told to look at the next chapter. So, really can't wait now. Okay, let's go then. Quadratic irrationals are the numbers like this, which may be a rational. You get them as the roots of quadratic equations with integer coefficients, unless those roots are integers or rational or whatever. Hence positive integer that's not a square. Good. The first step of the proof will be find a quadratic equation with integer coefficients having alpha as a root. I've just claimed it. Let's hope that it's true. The other root will have to be the conjugate of this. So now we know the sum of the roots is 2a and the product of the roots is difference of two squares, a squared minus b squared n or something. Off we go then. Multiplied out, sum and product, there it is, good, a squared minus b squared n. Rational coefficients, it's still rational. Okay, after multiplying by a common denominator for the coefficients, this becomes a equation. You can make those into integers if you like, and it's got the right roots. Good. Okay, it's the common denominator, fine, good, okay. This gives us a quadratic form, and the form has two special properties. Okay, its top graph contains both positive and negative values. Now here, okay, this is the bit where I need to be convinced that there is a separator. It's because the polynomial, I thought you could plug in nearby fractions. Let's see what they do. It takes negative values, right, when z is between the two roots. Yeah, okay. There's some bit of, they're thinking about the real line, an interval on the real line, but with our projection method, that projects onto a bit of the outside of the fairy circle, and that bit you get negative values around there. There are regions associated with those points. Fine, yep, okay. So it wasn't look nearby. necessarily. I mean, that would work, but fair enough. Okay, opposite sign, signs of a quadratic, values of a quadratic. Very nice. Okay. Yeah. Okay. So a little bit of overkill maybe to explain the. I feel like I've got it now. Good. The rational numbers where the left side of the equation is positive or negative. Oh my goodness! Look at this. Has both sides. Okay, they're doing the switch between Z. Loads of work switch between fractions and coordinate pairs. Okay. Right, the top graph does not contain the value 0. You can't actually solve this for any rational number because we've already found all the roots of the quadratic. Let's go. Supposed to repair with this, we can have y at 0, otherwise x would also be 0. Yeah. Since y is a non-zero displaced, we're going to take x with a rational root. We've already found those roots that are irrational. Good. Okay. We will show theorem 5.2. Fine. Okay. Every form has a periodic separated line in its double graph. Fine. Okay. This corresponds to infinite periodic strip in the Ferrier diagram. Good. And then there's going to be this bit to try and piece that together in terms of what the continued fraction is, which is the thing this chapter's been telling us about so far to sort of motivate why we might care about theorem 5.1 and theorem 5.2. But the ends of the periodic strip of a hyperbolic form, new word, maybe? Just means it has roots, I think. Are at the roots. Yeah, good, okay. This seems true to me. Define, so it's periodic, so define the transformation, and then you'll go towards a fixed point, I think. Yeah. Oh, even better. Okay, as the values form cycle through finitely many values because it's periodic. We just had this for the particular example. It follows that the values of the right side of that equation go to 0. They're approaching a root. There are two ends. There are two. Ooh, ages ago we had a chat about how the two ends of the strip go to different irrational numbers. Yeah, that's all separated by the stuff that's happening in between. Two roots of that. Fine. Okay. Finish the proof of proposition 4.1, comparing two infinite strips with an end at the root alpha. One infinite strip is the strip given by the continued fraction for alpha. This strip consists of all triangles in the upper half plane Ferrier diagram that meet the vertical line through alpha. Yes, I remember this. It was above any. So now we're switching to the upper half plane Ferrier diagram. So there's another diagram that's related to all the other ones. You look above, you get infinitely many triangles. Infinite sequence of triangles. The other infinite strip is the one corresponding to the separated line of the form, which has end alpha by the lemma. The ends of both strips alpha eventually coincide. Since the analysis of infinite strips in section 2.2, I don't really like it when they refer to things ages ago that I wasn't really paying attention to. That's my fault for the record. You get timed out, not bad. Sorry, I'm catching up with chat. Chat is talking about my attempts to ban people selling views. But you currently, I think, just get timed out. Yeah, like Sensation Black is still here, or at least they were just after they got timed out for 1 second by the auto mod, which hopefully didn't traumatise them too much. Drama. Right, okay, I've interrupted a proof because it's I'm reminiscing about section 2.2, which I remember being slightly hand-wavy, maybe that's my hazy memory of it. Eventually consists of the triangles meeting the vertical lines of the irrational numbers at the end of the strip. The continued fraction is eventually periodic since the periodic strip that is periodic. Feels like a tautology, doesn't it? I was sort of taking it as read that these things were the same. What is this trying to tell me? Yeah, no, I don't get this. I've been taking it as obvious that the thing that we're doing along the separator line, that looks like the kind of triangle picture that we drew for the continued fractions, and I know where it's going. And if it's periodic, then I think the continued fraction is periodic because you can read it off the picture. I don't understand these two strips, and it's asking me to think about another diagram, which is annoying me. I've already got 2 sorts of diagram, maybe 3. But the drama is just people. I think the drama is just banning people in chat. Did I ban someone? Oh, I said the word. I'm going to have to say the word on stream. The drama is just the bots are evolving, and I'm still bad at banning them. Right? I didn't miss some drama, did I? Did I miss drama in my own Twitch chat? Oops. It's a bot drama. Phew, good. Okay, had me worried there. The drama is we've split entirely. We're now two separate chats. You don't. No, of course not. Right. Okay. I didn't really understand that, and I feel grumpy about it relying on a thing from ages ago that I don't remember, and a thing from the future which I haven't seen yet. But hey, apparently you can put those two things together. We've been told in the middle somewhere the two things go together really nicely to say that continued fractions in certain situations are periodic. What's in 4.3 is these are the only ones. Okay, that's a little bit better. Let's have a look at that. Proof. Consider first this continued fraction satisfying those properties. There's going to have to be a number root p over q apparently. And is the proof going to be something like, I'm not looking, the proof's going to be something like, aha, these are exactly the properties needed to set up periodic, symmetric strip in the fairy diagram, and we just analysed those as one of those. No? Oh my goodness, right, okay. For the positive number 8n, reciprocal, oh my goodness, what are we doing? And the reciprocal of this is q over p, so it's positive, oh my goodness. Okay, just look at these ones, fine, okay. Confuse. No, carry on. Okay, good. Satisfying the palindrome condition of the relation that machine n, the length of the period is even, so it's doubling the period to give a fraction. Yes, good. Okay. Fine. I think that's allowed for glide stuff, right? Maybe? No. I don't know what that's doing. Okay. Hello, Batman. How are you doing? Good to see you. Welcome to the stream. We're doing chill maths. I'm trying to understand something that's not very chill because we've gone in proof mode and it's trying to prove something. Thank you for the follow. Yeah, we don't always do continued fractions. Sometimes it's fractals. To be honest, I think Twitch prefers the fractals. So might have to plan more fractal content or make this content look more fractally because my quest is to try and understand this number theory book. Right. This being advertised, the army, constantly. Some things never change. Good. Okay, what's going on here? Is this a long proof? What are we doing? I didn't ask for this, did I? I just want to see chapter 5.1, I think, which contains the other half of the proof I just read. Somehow. Facts from the future. Yeah, it's going to talk about, combining the strip. This is what I was trying to say out loud, I think. Combining the strip with its reflection gives an infinite strip with mirror symmetry. Hooray, it's the sort of thing we were just talking about. It doubles up this thing. It's periodic, and those are the ones we were talking about. The other end of the double strip converges to bar the conjugate. Since we've seen that two points satisfy a single quadratic equation, yeah, we had this thing that this is actually the same equation. Going the other way, you get the same equation. It's a quadratic, it's got two roots, it'll be okay. But you only have to solve one quadratic to get the two roots. Also, negatives of each other by the mirror symmetry across this. So now your quadratic form has to give you the same values on the other side. You're going to kill the xy term or something. Oh no, there's this. It implies that a is 0 when you do your conjugate. Oh, even better. Good. So the sum of the roots is 0 or something like that. Yeah, good. Square root of this number. Brilliant. Right, okay. I feel like they're doing proofs now, though. I haven't really seen. Have you any words to add? Right, we're ploughing through this to try and get to a symmetry point, but also finding out what they want to do in between. Oh my gosh, we have so many proofs now. Every periodic line in the dual tree of the fairy diagram. Of the fairy? Probably the fairy diagram. Is realisable as the separator line of some form. So if you take this big binary tree thing that we've got going on, big binary tree, and you just write a kind of short, repetitive poem about how you're going to go left, left, right, again and again, left, right, through the binary tree, does that necessarily give you the separated line for some quadratic form? Are you getting close to the roots of some quadratic thing? You probably are. It's the proposition. You do this, whatever you choose, you do it again and again through the binary tree. Or the dual of the binary tree, so who knows? I mean, it says dual tree on the screen, so whatever. Backwards and forwards. Where are you going? What are you doing? And the magic is going to be that after you've done your repetitive poem sort of thing about how you're going this much, a result of that is just that you've applied a linear transformation. You did a whole dance about it going through the binary tree, but you're doing linear transforms each time. You're doing some sequence of them that's going to be a big linear transform. And now the stuff forwards is a linear transform of the stuff you had before. Because every point that you're visiting is now sort of linear combination of where you put your sequence of left and rights. Each one corresponds to adding the numerators and the denominators, or subtracting them. Something like that. Just left and right in this tree. It's the thing I'm not really getting. Sometimes you can subtract. What's left and right in the tree? Is it a tree of fractions or a tree of regions? What's going on? There are triangles which must correspond to points that you might put in. No, the triangles are just triangles. They're nodes, they've got degree 3. But they separate out regions. The regions correspond to the values you might put in. Oh, this is crazy then. So we've got a binary tree. I'm getting there, I think. We've got our binary tree. It's connected to another one up here, but let's try not to think about that too much right now. So we've got our two binary trees joined together in the middle so that everything's got degree 3. And these points correspond to triangles in the original fairy diagram. But the regions correspond to actual fractions. So, well, I say actual fractions. Let's go pairs of coordinates. So, what do you actually do with these things? So why do you draw in -1? So I know that you put in 1, 1 over here for this region in the middle here. So this region in the middle corresponds to 1, 1. Why do you put a negative number in there? What are you actually doing? As you go down, you're doing... I suppose you only need the median rule to get to sort of 2, 1 in here, adding. You can add these two to get down here. You just sort of keep adding 2, 1, 1, 2. You just keep adding. This is a tiny picture, I'm sorry, but this is 2, 1. This is 1, 2. So what are you adding each time then? You've got some plan to go dancing through this binary tree, left, right, left, left, right, right, left, right, left, right, all the way down. I do pronounce it fairy diagram, I know. I don't know, it's spelt like this. I am saying fairy diagram though. Cha-cha. Left, left. As you do that, the things that you're adding together on the way are... So it's related. If you have a string of left turns, maybe around here, then you're kind of hugging the left of this binary tree for a bit, which means that you've got this big region on the left which stays the same, and you're adding as you go the other thing that you had. So yeah, we thought about this kind of device before with a kind of mangle with 2 controls, which start set to 1, 0 and 0, 1. And something you can do is so the kind of left and right instructions are yes, you can add these. You have to add them. We're always adding. You can add them but then you have a choice about whether the thing replaces the thing on the left or replaces the thing on the right. So if you choose to add them and put the sum over here, then you can do that again. You can keep sort of turning that handle. So we'll add them and get 2, 1, and replace it over there. Sort of keep going. But maybe after a while you get bored of generating these things, and you want to add them. So I'll get 4, 1 next. Maybe let's add them and put that over here on the left. And maybe I'll do that a couple of times. And then I'll get bored because, oh no, I've added it incorrectly, right? So 7, 3, 1, 4, 1, but then 7, 2. Maybe you get bored of that, and then it's time to repeat your pattern again. Repeat your choices. Do you replacing the one on the right, or replacing the one on the left? So this dies, this dies, this dies, but then I decided to start replacing the thing on the left for a bit. And as you do that, you're doing a kind of linear thing each time, which corresponds to some matrix transformation. And you could say you're swapping them and always replacing the one on the left, or you could say, well, there's 2 things I could do here. And then matrix transformations, in some sense, if you store these 4 numbers in a matrix, then you can think of this as a matrix operation. So the whole big pattern of what you're doing is matrix operation. We're getting there. Right. Wait, first time track. Matrix Man 1 wants arbitrary powers of 1, 1, 0, 1 without induction. This is strongly related to what we're doing, because that's what matrix is relevant. Right, Matrix Man. How long was that? How long ago was that? Was that a minute or 2? Sorry, I hope you're still here. Watch this. So without induction is an interesting restriction. But let's go. So first, I'm just going to do some powers because I think you'll enjoy. Wait, no, hang on. This one's easy, isn't it? Yeah, you should just do this one, right? You should just do this one. I think this is nice, right? I don't know. So without induction, we're going to be a bit stuck, aren't we? Because this is telling us that we need to add numbers together. 1, 1, 0, 1. By random coincidence. I don't know if you joined this Twitch stream on purpose or something, but by random coincidence, the numbers that you're generating, by the way, 1, 0, 2, 1, 3, 1, they're precisely the numbers that I was just generating up here. Because if you keep going, look, then 1, 1, you get 3, 1 over here. And as you keep going, the only thing that's changing is this number over here. So I don't know how I do that without induction, really, because it's such a sort of, wow, you have 3 of them and you get a 3 here. Perhaps, I don't know, perhaps you would like to do it as a transformation. So in 2D, this says that the basis vector 1, 0 stays still. So this vector doesn't get changed by this transformation. But the basis vector 0, 1 gets mapped to 1, 1 over here. So it was here, and it gets mapped over here. So everything gets sheared, so that what was a square grid becomes this kind of diamond grid. Shear. So you've just taken a square grid and given it a shove, so that it's now diamonds. The question you've asked me is powers of this, which is just going to be doing that lots of times. So keep shoving. And if you shove it n times, then, well, this thing over here is going to go n points over there, isn't it? So we started with this vector down here never changes. It's not affected by your transformation. And this one up here, 0, which was 0, 1, originally the basis vector for a square grid. Each time you apply your transformation, it gets sheared. So shear like this, right? Oh, let's get the direction right. Shear like this. So the top's going that way, and the bottom's going this way. This grid extends out this way, right? What's happened? Shear. Shear. There we go. Shear like that. If you do it n times, then it's just gone over there. Can you do it with matrix diagonalization? Sadly, no, because this matrix is not diagonalizable. It doesn't have enough eigenvectors. So matrix diagonalization is a good trick, and it's why I looked with glee in my eyes that we can just do this with matrix diagonalization. Oh, you want to do it with, but taking a limit. What's this? Oh, I don't know why you do that, to be honest. Why would you do that? So what do you want? You want to break this by having some transformation where you also have some eigenvectors, maybe with some scaling to change one of the numbers a little bit and then take the limit. I don't know, it sounds dangerous. It's not what I would do. Yeah, in general, some matrices are diagonalizable, some of them aren't. Is this even true? Are there matrices kind of nearby? Is it even true that the nth power will be nearby? It's probably fine, isn't it? If you have a matrix that's a slight, tiny bit away but can be diagonalized. So probably you change one of the numbers, not the top right one, but if you change this one to be not 1, possibly that's diagonalizable. It's got distinct eigenvalues. Must do, just generally. So then you're fine. I don't really know what that does. Well, transformation would send it to slightly bring it down a little bit as well. Why is that good? Because then it's got eigenvectors and you can just work out the power. Feels dodgy. I don't know why, but it feels like if you're happy to mess around with the limits of these things, passing them through your powers, well, it's finite powers, you're fine. But if you're happy to mess around with the limit, then shouldn't we just calculate some powers and use induction? Wouldn't that be nicer? Hello, Fizzbuzz in chat. He says Topology of Numbers, first time in chat. It is a fun book. You can get the book because it's free and it's online as PDF, which is what I'm doing. We've got all of the numbers arranged on the unit circle with a rule to join them up, so which is causing me a lot of trouble. Right, what was I actually doing? Oh, I was thinking about another way of explaining what we're doing based on matrix transformations. Can I turn those into matrix transformations? So something like, I want to add them. So I have A, B, and C, D. And I've seen some matrices in this book already, but let's see if I can recreate it. So I know I want to add them up, but I don't know if I want to replace the thing on the right or replace the thing on the left. Let's do the first one. So if I multiply by 1, 1, that will add them and put it in the right-hand slot. So I'll get A plus C and B plus D over here to add the things, vectors together, the column vectors together. And on the left, I'd like to keep A, B if we're replacing a thing over there. So keep A, B as this. Okay, or the alternative of what I could do is I could take A, B, C, D, and I could put the sum over here on the left. That's what I might do. I've written coordinates over here instead of vectors. That's just laziness, I suppose. 1, 0. Okay, so these are the matrices that I think we've seen before. So I think we're all right. Maths222 has gone and done some limits of matrices and things seem fine. I'm glad I didn't do it on screen. I thought I'd make a mess of it. See what are you doing? You're breaking the fact that it's singular. Maybe this is just a good idea. I don't know. You want to do the 1 plus epsilon thing and then calculate its eigenvectors. Seems like work. Okay. Right, okay, so I should just take powers of these. And this is the observation. It's going the other way. The inverses of these are a bit like doing Euclid's algorithm or something like that. There's some link to Euclid's algorithm in here. Oh, right, we're hitting 4 o'clock, which is when I normally stop. So let's see if we can get to... Let's see what's going on. What is this? There's some transformation. Yeah, okay, good, okay. Yeah, some rings. Yeah, it's going to be fine. I don't know how excited I am about this proof. That's a nice diagram on that side. Yeah, okay. Positive values of vertices in one arc, negative values of vertices in the other arc. Okay, right, I'm going to have a sort of skim look through. We're on page 105, which actually is 113 in the slider at the bottom of my page. There's some stuff with some more pictures, there's some exercises. Is this the end of 4? No, we've got Pell's equation next. So Pell's equation is going to tell us about solutions to this. I do want to know about this. Look, here's generating some solutions by working out the transformation T, perhaps. Yeah, periodicity transformation to work out how to get to the next solution. Good. What's this? So we get more of this. We got some exercises, and then is it time for chapter 5? Possibly. Then it's time for chapter 5. Hyperbolic form. Right, they used the word hyperbolic earlier. I thought that was alright. Okay, so possibly next time we go live, we can try and understand Pell's equation a bit. I should have a quick look at this. Mary gets points if I have a quick look at this. Yeah, let's decide how excited I am about this. Possibly not at all willing to skip it to get onto Pell's equation next time. And then the time after that, we finally get to see section 5. So if we have some, so this is telling me if we have some periodic, you do some cha-cha-cha dance through the binary tree thing, then there's a linear transformation, so you're going to be fine, or something. Okay. Okay, for some reason we've gone for this one. The translation given periodicity says this. So after you've done all of this dance, you end up at these numbers. That's the transformation, really. What's happening to your basis vectors? This matrix. So it's this transformation, fixed points of t established by. You get a quadratic out of that because numerator is linear. You're going to set it equal to z, which is then going to give you t of z equal to z, which is going to give you a quadratic. The roots of the fixed points, we do not actually have to compute them. This example, yeah, so we just want this quadratic form. Seems fine. Compute as a check, compute the separated line of this form. Hello, here it is. A realization of the given periodic line of the separator. Any constant multiple of this form would also have the same separator line, since we would just be multiplying all the labels along the line by the same constant. Okay, fine. Going to simplify the calculation in this example by observing the periodic line we started with was taken to itself by glide reflection. Only half as far as long. So glide reflection is this, has the same fixed points. As we have this, simplifies more directly to the same equation. That is good, isn't it? An odd number of terms of the continued fraction and then a repeat. I think. Yeah. Okay, right. Too cool for exercises. So it's bad role model, really. Ooh. And it's 1, 2, 3, 4, 5. It's the continued fraction. But I think let me just go for it. Just go and do it. And we've got other ways. Just go for it. Yeah, it's kind of like you go and do the calculations, and it's not obvious to me that you need any of the diagrams when you're doing the calculations. You just kind of follow the rules. So I think I'm more interested in section 5.1, but anyway. Find a quadratic form whose periodic separated line has the following pattern. So the pattern relates to the continued fraction, so we should be able to put numbers on it. It's quite tempting to just put ones on it, but that wouldn't satisfy the arithmetic progression rule. So you'd have to do something else. Oh, right, and then do it in general. Fine, okay, that's quite nice. Maths 2 in chat says that they've used. Oh, they're talking about matrix power things. Matrix powers. Good. Okay. Fizzbuzz is doing some powers as well. No, wait, what is this? E might be epsilon or something. I'm just worried that this thing is going to go singular, isn't it? I suppose maybe it works in the limit and you're all going to convince me it's all okay. Well, I think that is going to be a way to wrap up. I'm going to quickly think about glide reflections while looking at this picture. It does have a glide reflection, doesn't it? 3, 1, 2, and then 3, 1, 2 the other way up. 3, 1, 2, and 3, 1, 2. So how does this transformation work then? Oh, so if you transform it properly, then Periodic just means that the top is periodic as well, so you can just wait for it to go 3, 1, 2, and then wait for the 3, 1, 2 on the other side, and it's all fine. So you could think of this as being periodic along here. So this 3 is then repeated over here. You're missing the trick that it's flipped and repeated the other way up. But that's okay. I'm right with that. Yeah. All cases except when the bottom left corner is non-zero, it's all okay. Well, there we go then. Okay. Matrix calculations. Verified by Twitch chat. Good. I thought that was brilliant. The matrix question came in just when we were thinking about doing some sequence of numbers that corresponded to exactly the ones in their question. I thought it was amazing. I'd just crossed them out actually, but there were 2, 1, 3, 01, 11, 2, 1, 3, 1 down the right here for a matrix transformation, which was, we eventually decided, exactly the matrix that appeared in chat. That's one of those occasions, isn't it, where I hadn't quite calculated the matrix. Chat turned up with a maybe unrelated question, which was the matrix I was looking for. Maths. What are you going to do? I would love to do powers of this, because that corresponds to walking through the fairy diagram, generating a very, very periodic sequence of numbers. Right, good. Okay. I think I'm going to wrap up there. Am I here next week? It's one of those questions that we can ask, isn't it? I think I probably am here next week. Yeah. Where else would I be? Oh, I'm probably not here in 2 weeks. Or 3. We've got an Easter break. But we've got one more. Pell's equation, possibly. Oh no, that means I'm not going to see chapter 5 for ages. We'll have one more next week before a bit of an Easter break. Take care, everyone. Have a nice afternoon. Have a nice week. Just absolutely to each their own. Right, okay. See you in a week for more chill maths. Thanks for helping with me understanding all of the diagrams, all of the dual diagrams. Right, yep. I am finishing the live stream now.